Hi guys, myself Pranav is here to deliver today's presentation, Power Transformer Part 46. As the subject is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with series capacitors in transmission network. Series capacitors are installed for series compensation of the transmission line. The series compensation method is the most economical as well as much more efficient method for improving power transmission capability of the long, high voltage, extra high voltage, and ultra high voltage lines. Benefits of implementing series capacitors are as follows. A, to enhance the power transmission capability. B, to improve the system stability. C, to reduce system losses. D, to improve the voltage profile of the lines. E, to optimize the power flow between the parallel lines, that is optimization of load sharing between parallel lines. F, cost of a series capacitor bank is more or less 10% of the costs for implementing a new transmission line. Hence, there would have been a few years' time to pay back. Series capacitors are actually applied for compensating the impedance of transmission line. It has already been exhibited that the demand of reactive power would basically always be more at the load side of the power transmission system. That is the reason for which capacitors should have to be placed as close as possible to load side. That helps to generate reactive power, which in turn would help to maintain the voltage stability at the load side. Power capacitors are thus to be used in series or shunt connections and are typically employed in power network for different process applications such as voltage control, power factor correction, filtering of harmonic response, and reactive power compensation, the most important one. Comparative study of applying series capacitor and shunt capacitor. Number one, to improve the power factor and voltage. Once an inductive load is connected to the transmission line, power factor lags because of lagging load current. Again, I repeat, once an inductive load is connected to the transmission line, power factor lags because of lagging load current. Shunt capacitors, once connected, would help to draw current leading to the source voltage. So, using of shunt capacitors are of much more reliable in case of stabilizing the system, improving the power factor, and increasing the line voltage. Series capacitors, once connected with lines, would have to compensate the inductive reactance, and sometimes that compensation might have been partly or fully depending on the capacitors connected in series with lines. The resultant effect is to minimize or even suppress the voltage drop as caused by the inductive reactance in the circuit. Now, see the schematic diagram. A series capacitor that has to provide automatic and instantaneous voltage rise as and when the load increases. See the diagram. How it will increase? Impedance, total impedance Z equals to R plus J XL minus XC, where R is the resistance of the circuit, XL is the inductive reactance of the circuit, XC capacitive reactance. A series capacitors would have to produce more net voltage rise than a shunt capacitor at lower power factors. Shunt capacitor would have to create more voltage drop, but would have much efficient in improving the power factor than that of the series capacitor. These 2 points are very important because it creates something different. For the series capacitor, it would have to produce more net voltage rise than shunt capacitor at lower power factors. And shunt capacitor would have to create more voltage drop, but would have much efficient in improving the power factor than that of the series capacitor. So, capacitors together in series would have to add up the voltages, and the consequent voltage boost is there to be proportional to the magnitude and power factor of the through current. Hence, in case of series compensation, that results in a voltage rise at the end of the feeder that varies directly with load current. Therefore, instantaneous boosting of voltage that would have been undertaken automatically whenever the load starts increasing. In contrast to shunt capacitor, a provision of series capacitor is comparatively less effective in improving the system power factor and also has the little effect on the source current. Shunt capacitors are generally applied to improve the power factor of the system, whereas series capacitors are generally employed to improve the stability of the system. While delivering the power via a long radial distribution line, then the line resistance and inductance are the two main components causing an increase in the voltage drop. However, the sudden interruption of electric energy as well as the voltage sag would have been the most significant power quality disturbances in the electrical system. To counter these problems, it has been exhibited that the series capacitor compensation method would have been the ideal characteristics to improve the voltage quality. To improve the voltage quality, you have to use series capacitor. A series capacitor, while is to be connected in the radial distribution grid, then the control of natural voltage that can be achieved only by alterations in the load current. Implementation of series capacitor would have been the most effective method where the voltage drop is the limiting factor. Reactive power. Number 2, reactive power generation. Series capacitors in the power system would have to generate reactive power which is proportional to the square of the load current. Shunt capacitors in the power system would have to generate reactive power which is proportional to the square of the voltage. This is the main difference. Series capacitors in the power system would have to generate reactive power which is proportional to the square of the load current, whereas shunt capacitors in the power system would have to generate reactive power which is proportional to the square of the voltage. Other factors. Number 3. In high voltage, extra high voltage, ultra high voltage transmission lines, series capacitors are mainly used for series compensation so as to enhance the power handling capabilities. While the shunt capacitors are being applied to an electrical system for entertaining multiple of tasks. Shunt capacitor banks are thus to be constructed as of the required system voltages and their selective parameters that would have to act both as harmonic filter and reactive power compensation. Shunt capacitor banks would have to act as a harmonic filter as well as reactive power compensation. Salient points regarding reactive power. Number 1, voltage control and reactive power management both are interrelated and of much importance as because the transmission system usually operates with constantly varying reactive power requirement as corresponds to the variation of the load level. Number 2, the reactive power requirement also relates with the actual perspective of generating power characteristics as well as time varying configuration of load pattern at the transmission network. Number 3, when the transmission system would have to entertain much more load than that of the voltage can support, then there may be a chance of voltage collapse or voltage sagging. Once the voltage starts to drop down, then the current must have to increase so as to maintain the required supplied power. As of the subsequent effect, the system that has to consume more reactive power causing to voltage drop further. It is a normal phenomena to exhibit that decreasing reactive power would cause voltage to fall, and with the increase of reactive power, there will be an enhancement of the voltage parameter. Therefore, the demand of the reactive power would have to depend on the quantum of the inductive load as connected at the receiving end of a transmission line. Again, I repeat, it is a normal phenomena to exhibit that decreasing reactive power would cause voltage to fall, and with the increase of reactive power, there will be an enhancement of the voltage parameter. Hence, in power transmission system, if there be a higher amount of inductive load as compared to other, that is capacitive load, then the larger will be the demand for reactive power. Most of the transmission systems are equipped with static compensators such as capacitors, inductors, and tap changing transformers, which may have to respond as corresponds to the changes in voltage support requirement. The nature of the reactive power should have been characterized in the process of operational condition, whether the equipment would have to withdraw the reactive power from the source or may have to supply reactive power to the source. Categorically, it can be made to justify by the conceptual aspects of existing load system operates at lagging or leading power factors. However, for a given load, if the power factor is lagging, which means the subject load would have to withdraw reactive power from the source. In contrast, for a given load, if the power factor is leading, that indicates that the subject load would have to supply reactive power to the source. Basically, series capacitor is much effective to implement when the total line reactance is found to be high. Number 15, installation of series capacitors are mostly recommended for extra high voltage and ultra high voltage line, where the load side reactive power requirement would have been considerably high. Number 16, series capacitors are of little use where the load side reactive power requirement would have been significantly low. Number 17, installation of shunt capacitors are mostly recommended for lightly loaded cables or lines. As of example, an induction motor has always been lagging power factor as because it withdraws reactive power from the source to fulfill its magnetizing requirement. The reactive power is essential for producing an effective evolving magnetic field. Again, I repeat, the reactive power is essential for producing an effective revolving magnetic field, which thus to be required for successful rotational operation of the induction motor. Right? An overexcited synchronous motor or capacitor bank has always been leading power factor as because it has to supply reactive power to the source. An underexcited synchronous motor must have to withdraw both the real power and the reactive power from the source. See the diagram. Generator source, load, this is the load, that is induction motor, the lagging power factor, power, overexcited synchronous motor, leading power factor to the source, leading power factor to the source, underexcited synchronous motor, lagging power factor from the source to load. Impact of reactive power. Reactive power flow would have been a salient feature of an electrical power system and must be mandatory for the operation of different types of load, either static or rotating. The reactive power is exclusively essential for supplying requisite magnetic circuits of machines, motors, and transformers. Specific value and flow direction of reactive power in transmission and distribution networks would have to vary according to load level and power factor. A higher reactive power means a higher apparent power, and thus for the same active power, there must have higher current to supply. As of the higher supplied current, this circulation of reactive power on transmission and distribution networks would therefore produce a number of undesirable consequences. In power system, it is indicated that most of the reactive power would have been consumed by the inductive loads, as well as the components of the network, such as transformers, synchronous and asynchronous motors. Excessive flow of reactive power in network must have to instigate several issues such as increase in power losses, worsen the system voltage, weaken the system reliability, and poor power factor. Undesirable consequences which are to be characterized. 1. Overload of transformers, higher temperature rise of the supply cables, additional losses, large voltage drops, higher energy consumption and cost, less distributed active power. In order to optimize and thus to enhance the stability of the power network, there should have to regulate the flow of reactive power by means of injecting capacitive reactive power, or otherwise by consuming through introduction of inductances. Based on the demand of the network, the reactive power that would have been injected by capacitors or consumed by inductors, both either connected in shunt or series with the circuit which is to be located nearer to the load side. To facilitate the supply power through a transmission system, the power transformers and generators both are to be designed for a specific apparent power in power systems. So, higher the reactive power by keeping active power constant, then higher will be the apparent power, which can contribute a significant loss of power through generation of heat with having low system power factor. Therefore, it can be concluded that A, if the network is comprised of resistive capacitive equivalent circuit, then the reactive power would have been generated. Again, I repeat, if the network is comprised of resistive capacitive equivalent circuit, then the reactive power would have been generated. B, if otherwise, network is comprised of resistive inductive equivalent circuit, then the reactive power would have to be consumed. Circulation of too much inductive reactive power in a network that would have been responsible for being a voltage collapse. Circulation of too much capacitive reactive power in a network that would have been responsible for being voltage enhancement at the load end of the line, which may have a cause of severe problems. Let's stop here. Further to be continued at later stage. Thank you for listening the video. Kindly do like, share, and subscribe. Your subscriptions would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section, please. Thank you. Thank you for patient hearing.